For our senior design project, we are developing a real-time operating system called Project Oxide. A real-time operating system, otherwise known as an RTOS, is an operating system that guarantees a certain capability within a specified time constraint. This is commonly used in situations where an operation has to complete within a specified time constraint, such as microdevices or kernels. These are the names of the people on our group: Daniel Wendelken, Dom Farolino, Codi Burley, Doug Flick, and advisor John Franco. Actually, Dr. John Franco. The goal of Project Oxide is to produce a real-time operating system that focuses on security for IoT devices. Oxide will be built from the ground up in a language called Rust. Rust is a system programming language that is fast, prevents seg faults, and guarantees thread safety. From this, Oxide will be hardened to prevent and mitigate many threats IoT devices face. Here are some of the user stories that we've written. As an IoT developer, I want a secure and operating system that handles real-world events in a known time frame. As a developer at a defense company, we need a real-time operating system that will be difficult for enemies of state to penetrate. As a developer at a conveyor belt company, we need to quickly sort items and ship them to a desired location as quickly as possible. As a developer at an aerospace systems company, we need planes that can handle environmental effects as fast as possible and safer from human programming errors.
When designing our kernel, we decided to look at it in terms of its input and output. So the possible inputs that we'll be supporting will be network input, so things through a network driver that we'll be writing custom, user input, things through the keyboard and the mouse and standard input, as well as application input, which would be user-produced binaries that will run on our kernel. The operations our kernel will be performing are broken down into several steps. So first we have applications running in user space that our kernel is going to manage. Then for the actual application manager portion of our kernel, we'll be focusing on process scheduling, memory allocation, and timers and clocks. These are three massive components to any kernel and have unique implementations in a real-time operating system. The kernel is reached from the board support package, which is essential code for any given computer hardware that actually makes the computer operating system work with the hardware. So in essence, it's the bootloader or the boot manager that the operating system uses to load itself into memory. And of course, all of this will be running on a target hardware of our choice. As far as our outputs, we determined that we're going to be working with two different outputs, which is going to be visible user outputs, such as text and images, and generated software data, such as user-produced binaries or text files. We've broken down the production of our real-time operating system into a series of tasks, the first of which is identifying a target hardware for our real-time operating system to run on. Next, we'll be researching previously designed real-time operating systems to identify the common architecture approach that the industry has taken, especially for those operating systems actually built in Rust. We'll then be researching attack vectors and common attacks that happen on real-time operating systems, especially the ones used in IoT applications. In order to get something running, we'll then be researching the board support package and getting a small bootable assembly program flashed to the chip. Finally, we'll be implementing basic kernel operations such as memory allocation and process scheduling, and then start performing red team penetration testing on our operating system to determine how secure we've gotten by default.
So far, most of our progress has come in the form of just general research or design. Specifically, we've looked into the hardware that we want to use for our initial implementation. We've looked at the ARM Cortex M series chips. This is a really commonly used chip, and it's something that we think we might be able to utilize in our own project. We've also looked into the bootloaders and how we might get that up and running, because that's going to be one of the first things we need to implement for our operating system. We've also spent time understanding process scheduling in real-time operating systems and how they differ from, say, a more traditional operating system that most people think about. Lastly, we've started to look into ways that our real-time operating systems are not safe and what the attack vectors are on those. We'd like to also look at IoT devices, because that was one of the focuses that we would like to cover in our operating system. As you can see, here's our divisional work for the tasks that we've laid out for the project. I don't think it's really of much use to read it off to you, but you can examine it yourself if you'd like. One notable thing is that we've decided to give each task mostly to one person. So that means, we've got someone with 75% and then 25% for each task, and that ensures that we don't muddy up one task too much, and then we get small efforts in each of these areas. All right, so that wraps up our progress thus far. We're pretty excited to start getting our hands dirty and get something up and running on some actual hardware. Also, thanks to John Franco for being an advisor for the project. We look forward to working some more with him. Actually, Dr. John Franco.